Okay, let's continue. We are at 33.3 plane electromagnetic waves. This is probably a pretty tough section to get through. A lot of equations, but we'll get through it. So let's share the PowerPoint. And we have the situation we've seen before. We have a surface S, and there's an electric field between the plates, so it creates an electric flux through the surface. Now we're going to look at the a plane electromagnetic wave. It goes in the direction of C, and it has vector components in the E direction along the Y and the B direction along the Z. And we're going to look at the equations and come up with the wave equation for this. So if you look at this little uh, figure in the corner, according to equation 3315, this spatial variation in E gives rise to a time-varying magnetic field along the Z direction. So if we look at integral of E dot ds, that's equal to the negative of d phi dt. In other words, it's a changing magnetic flux. And you can see the B in the green there. There's a so if we integrate in the counterclockwise direction on this little rectangle, we're going to get it's ex dx is approximately ex plus d e dx, where t is constant, dx, and that's equal to ex plus the partial of partial of x dx. And so integral of E dot ds is ex plus partial of E partial of x dx times L minus ex L, which is approximately L partial of E partial of x dx. Um, let's see, I think, yeah, okay. So the magnetic field B, the magnetic flux B is equal to BL dx. So d phi dt is equal to L dx dB dt, where x is constant, and that's equal to L dx partial of B partial of t. So L partial of E partial of x dx is equal to minus L dx partial of B partial of t. Oops. So partial of E partial of x is equal to minus partial of B partial of t. Now, the integral of B dot ds is equal to uh, epsilon 0, mu 0, the permittivity and the permeability of d phi dt. Now we're looking at the magnetic components. And integral of B dot ds is equal to bx L minus bx plus partial b partial of x dx times L, which is approximately minus L partial of b partial of x dx, equals phi e, the electric flux equals E L dx. So the partial of the electric flux dt equals L dx partial of E partial of t. Let's get back up here. Partial of E, if we take the partial of electric flux with respect to t, and that's equal to, if we take this equation, the partial electric flux dt equals Lx partial of E dt, and we take the equation integral of B dot ds is approximately minus L partial of B dx, or partial of x dx, and we put it into this B dot ds equals mu sub 0 E sub 0 d electric flux dt, we get minus L partial of B partial of t dx equals mu 0 epsilon 0 L dx partial of E partial of t, which we get partial of B partial of x equals mu 0 epsilon 0 partial v partial of t. And the partial v partial of x equals minus partial b partial of t. We get partial e squared over partial x squared equals minus the partial of x of partial b divided by partial t equals minus partial t of partial b over partial x equals minus the partial of partial t equals minus mu 0 epsilon 0 partial v partial t, and that gives us the partial squared of e over partial x squared equals mu e partial squared e over partial t squared. Now, this is reminiscent of the wave equation that we looked at in minus 16 in chapter 16. If let's see, did I? Oh, all right. I have that. Oh, well, I don't have my things set up, but you can look at the. See if they say which equation it is. 1627. It's 1627. It's the linear wave equation. So we have partially partial squared e over partial x x squared mu e mu 0 e 0 partial squared e over partial t squared, and we get partial squared b partial x squared equals mu 0 e 0 partial b over partial t squared, and there's the 1627, the wave equation. That was for acoustics. Partial squared y over partial x squared equals 1 over v squared equals partial squared y partial t squared. So if we call c, if we substitute 1 over c squared, we see that 1 over c squared is equal to mu 0. So c being the speed of light, is equal to 1 over the square root of mu 0 epsilon 0. So c, the speed of light, is equal to 1 over the square root of the permeability and permittivity constants, mu 0 epsilon 0. So if we calculate that out, the c equals 1 over the square root of 4 pi times 10 to the minus 7 Tesla meters per amp, and the permittivity constant 8.85419 times 10 to the minus 12 Coulomb squared per Newton meter squared, we end up with 2.99792 times 10 to the 8th meters per second, which is the speed of light. Excuse me. So if we take these equations, partial square root of e over partial square root of x equal mu 0 e 0 partial square root of e over partial t squared, and so the electrical equivalent and the magnetic equivalence, partial squared b over partial x squared equals mu epsilon partial squared b over partial t squared. We get some equations. E equals E max cosine kx minus omega t, and B equals B max cosine kx minus omega t. Now, omega is, as we know, 2 pi f, 2 pi times the frequency, and k is equal to 2 pi divided by lambda, the wavelength. And we can see that excuse me, lambda times f is equal to c, the speed of light, and that's not anything new. If you can manipulate our old distance equals rate times time, or in this case, um, distance divided by time is equal to speed, where lambda is the distance, it's the wavelength. Frequency is 1 over the period, so that's 1 over time. That's equal to the velocity, meters. So you can have lambda in meters and period in 1 over seconds, and you end up with meters per second. Okay, the partial v partial x gives you minus k e max sine kx minus omega t, and partial of b over partial of x gives you minus kb sine kx minus omega t, and that gives you, oh, I missed that part, partial of e partial of x equals minus b partial of t, so ke max equals omega b max. So E max over B max equals omega over K, which equals speed of light again. So E max over B max equals E over B equals the speed of light, C. And this is what a wave looks like. And you can see that when E is max, B is max, and here we show that if it's propagating, if the wave is propagating in the x direction, and you can see that it alternates as it propagates. You can see that it alternates the B field from the plus z to the minus z, plus z to the minus z, and the E field is plus y to the minus y, plus y to the minus y, alternating, but they're always in phase. In other words, when you're at E max, you're at B max. When you're at negative E max, you're at negative B max. So there's zero phase between them. So now they are orthogonal. In other words, if the B vectors are like this, if the E vector is like this, the B vector is like this. They're orthogonal. But when you have E max, you have B max, so they're in phase. What is the phase difference between the sinusoidal oscillations of the electric and magnetic fields in the figure? 180, 90, 0, or impossible to determine? Well, I just told you they're 0. In other words, they are in step with each other. When E is max, B is max. When E is 0, B is 0. So there's 0 phase difference between them. Now, an electromagnetic wave propagates in the negative y direction. The electric field at a point in space is momentarily oriented in the positive x direction. In which direction is the magnetic field at that point momentarily oriented? Well, if it travels in the negative y and you have positive x, the other is going to be in the positive z direction. You can, in other words, here it's going in the negative y, but if you, the electric field, if it's going in the negative y, the E is in the positive x, the B is in the positive z. I hope you can see that. Okay, we'll stop it there, and we'll go on with the next section, energy carried by EM waves.